Hi, everybody. So today we are doing our topic 17 study group on Bayesian statistics, and there are two main things that I want to talk about today. I want to walk through the process of solving a probability question using Bayes' theorem. And then I am also going to be walking through the concept of maximum likelihood estimation. I forgot to share my screen before I started, but to start, let's start with a probability question. And at any point, we're going to go through mathematical processes of solving a probability question. So if at any point you have any questions or like I'm going through some equations too fast, we do have time. So just let me know and I can definitely break things down. But this is the question I'm going to go through today. This is on your labs. And also if you go into our DS concept questions doc, there is a similar question, just different numbers. So I highly recommend after today, and I go through the process of solving this, see if you can solve this question. So I already gave you the answer, 1/3 or 33%. Apply the same methods that we use to solve this question over here. You should get that correct answer. Why that is important? Honestly, I'm not sure why, but out of all the probability questions, that is the harder one, but also that's the one that I've been asked the most out of any of the other probability questions. So I do think it's good to know. Also, we'll preface with those were very like quantitative heavy jobs that did require more like of a math background. So just for your information. So this is the question that we're going to go through. And through this question, we're going to encounter two main things. We're going to encounter Bayes' theorem and the law of total probability. And I'll break these things down as we solve this question. So let's go through this question just for context. So there's a diagnostic test and it is advertised as being 99% accurate. So you have to be very careful, especially when we get into later phase material. What accurate means, there's a very specific definition of accurate. In this case, they actually break it down for us. So if a patient has the disease, they will test positive 99% of the time. Now, if they don't have the disease, they'll test negative 99% of the time. So just 1% of the time, depending on whether they have the disease or not, the test will just give an incorrect indication. On top of that, 1% of all people have this disease. So the question they're asking is, if a patient tests positive, what is the probability that they actually have the disease? So without looking into probability, a very common incorrect answer is 99%. And you can sort of see why people would say 99%, right? Because if they test positive, probability that they have the disease, it sort of looks like this. If the patient has the disease, they'll test positive 99% of the time, but that's slightly different. If you look at, they sort of give it away a little bit over here. You're looking for disease given positive test. Later, as we set up this question, you'll see that this is not equivalent to this probability over here. Rather, this is equivalent to the flipped probability. This is actually what's the probability of getting a positive test given that you have the disease. We'll set that up later, but any questions on this setup before we get into the math of it all? All right, I'm personally very excited about this because I spent many years just doing math problems, so this is exciting for me. Okay, I'm going to be sharing. Oh, yeah.
Is this something you could represent with a tree diagram?
You definitely can. Yeah, absolutely. Okay. You can represent it with a tree diagram, which actually makes it slightly easier because you don't have to then use the theorems directly, I believe. However, I haven't done this in the tree method in a while, but I'm not sure if you have all the information in the correct order that you need for the tree. I'm not going to walk through that currently, but happy to talk about it at a one-on-one next week if you'd like. Okay, cool. Awesome. Okay, I'm just going to reshare this whiteboard screen. So I have a white screen over here, and we're going to walk through how we solve this question. So when given a math question, what I like to do is just write out what we have to start. So just to simplify things, we have two events that are going on. One is you either have the disease or don't. The other, which is kind of independent, is the test that you take, whether it tests positive or negative. So these are kind of two different things at play. So just to make it easier for our notation, we're just going to call event A having the disease, and event B is testing positive. Just to make it easier for us. Okay, So what other information are we given? First, I think the easier one to go to like define and just write out is that the probability of having the disease. So in the question, and it's hard for me to like keep switching over, but part of the question says that 1% of the entire population has the disease. So independent of the test, the probability of having the disease is 0.01. That's information that we have. So next, in thinking about that 99% accuracy, in that 99% accuracy, they said that, and I actually have it over here. Sorry, I can't share both screens at once. But if the patient has the disease, they will test positive 99% of the time. So given that they have the disease, they will test positive 99% of the time. So how do we represent that in our probability notation? Given that they have the disease, they will test positive 99% of the time. So that's information that we are given in the question. Something else that we're given is the opposite. Given that they don't have the disease, so don't have the disease, they will test negative 99% of the time. And what we're trying to solve here is what is the probability of having disease given that you tested positive. So this is what we're trying to solve for. Questions of this setup. I will admit that I have the answer to this written out on my screen. So it's not like I have these processes memorized, but also it does take a little bit of getting used to and like thinking about how do you translate the words in a problem to probabilities like this. It does take a little bit of practice. Sometimes you just have to get your mind into that probability state. But any questions on this setup so far? Okay. If at any point you have any questions, please interrupt me and let me know. So there are two things that I mentioned that we're going to use. We're going to use Bayes' theorem, and I'm going to write down Bayes' theorem in a little bit. Actually, I'll write down Bayes' theorem first, and then we'll go into the law of total probability. So what is Bayes' theorem? Bayes' theorem is a formula that is pretty neat, and this is Bayes' theorem. If you want to find the probability of A given B, it can be represented by this formula. Immediately, something that I like to think of when should I use Bayes' theorem? Something that I like to take note of is the flipped conditional probability. So you can see here A given B, and part of this equation is B given A. So knowing one, you can sort of use Bayes' theorem to calculate the other. And that's kind of what we have here, right? We are given B given A, and we want to calculate A given B. So this is kind of a hint that we need to use Bayes' theorem. I'm going to take like a mini little tangent and talk about where Bayes' theorem comes from. Of course, it comes from this guy named Thomas Bayes, just the father of Bayesian probability theory. But there's some pretty neat equations that you can derive to get Bayes' theorem. So back in topic 11, when we first introduced probability, we had the conditional probability formula. I'm going to erase this later on, but the conditional probability formula is basically that the probability of A given B is equivalent to the probability of A intersect B over the probability of B. So if you remember, another way I like to think of this is probability of A given B. And if we have a Venn diagram over here, and let's say this is A and this is B, probability of A given B, I like to think of it as what proportion of B is also A. So that's how I like to think of A given B. Maybe helpful, maybe not. Okay, so let's flip this around. Probability of A given B is given by this equation over here. What about probability of B given A? B given A, we just have to flip the letters around. B intersect A over the probability of A. So if you're familiar with like manipulating mathematical equations and also just knowing how intersect works, you can see that this top part and this top part over here, these two things are exactly the same. So therefore, in rearranging this equation a little bit, you end up with probability of A given B multiplied by probability of B is equal to probability of B given A multiplied by probability of A. We're just kind of equating these two things, this thing here and this thing here. And then in rearranging that, that's how you get to Bayes' theorem. So I thought it's pretty neat. I just thought that that's like a easier derivation to do. And yeah, that's how Bayes' theorem comes about. Okay, we don't need this for now though. But Bayes' theorem, I would say that like, if you're preparing for like a more quantitative job interview, Bayes' theorem is a good one to just remember that exists. So, okay, Bayes' theorem, and we know that we want to use it because we have the flipped conditionals. The fact that we want to find A given B and we are given B given A gives us a hint that we want to use Bayes' theorem. So let's plug in the numbers that we have. So A given B, we can plug in B given A, which is 0.99. We also know the probability of A, which is 0.01, and then divide it by probability of B. So currently we do not have this. So we're kind of stuck here, but this is when we're going to talk about the law of total probability. So we don't have probability of B, but we have all these other things. Let's talk about the law of total probability. The law of total probability, I'm just going to call LTP for now, states that the probability of A is equal to A given B multiplied by probability of B plus probability of A given B complement, B complement. I will say this is a formula that I almost never memorize. I just happen to have it on my screen as well. But this is the law of total probability, saying that if you know these conditionals, and then also the given part, these two, as long as they add up to 1, you can find the probability of A. If that thinking doesn't really make sense, then this is just a formula that's just, you know, good to maybe right before like a more quantitative interview, just remember. So, okay, this gives us a formula to solve a probability of A with all of these givens. But instead, we don't want A, we want to do B. So let's just replace all of these. Let's just flip the A's and B's so that we can solve for probability of B. So let's do probability of B is equal to the probability of B given A multiplied by PA plus the probability of B given A complement, probability of A complement. Cool. So we're getting closer and closer. So let's plug in the numbers that we do have. First of all, B given A and A, we do have these numbers. So 0.99 times 0.01 plus we don't have this yet, but I want to talk about this in a little bit. We know that A complement is 0.99 because A complement is just 1 minus probability of A. So you know it's going to be 0.01 multiplied by something else times probability of B given A complement. Cool. So right now we've gone from not knowing what probability of B is to, okay, we can sort of figure out what the probability of B is if we just had probability of B given A complement. So from here, where do we go? How do we figure out this?
0.99 times probability B given A prime.
Let's see. Let's see, probability of A. Oh, yes, you're right. Sorry about that. Yes, because A complement, I kind of flipped it around. Yes, this probability of A complement should be 0.99. Thanks for the correction. All right. Okay, so where was I? We want to talk about how we find probability of B given A complement. So something that's good to know, and the reason why when I think of conditional probability, I like to think of what proportion of B is also A. Let's take a look at conditional probability again. And mainly I want you all to take a look at this one over here. So a pretty neat formula to remember, or something that's just good to kind of conceptualize, is if we have B complement given A complement, and we want to find the complement of that, so basically this is equal to 1. So as long as these given parts match, these add up to 1. One way to think of that is, let's just say that A complement is this circle over here. And let's say that we have this square divided into half. Let's just say that this whole left side is B and this whole right side is B complement. So I like to think of this as, and let's say that for this purpose, let's just say that the circle is actually A complement. So this is what I like to think of. What proportion of A complement is B complement? That's here. And then what proportion of A complement is B? That's over here. So that just adds up to 1. I don't know if that was maybe more confusing or not, but just know that if you want to find like complements with conditional, as long as the given parts match, you can just do 1 minus. So based on that, we now know that because this is 0.99, this value that we need to figure out over here, oops, I meant to erase that. This value that we want to figure out over here is 0.01. So we have 0.01 times 0.99. And that is our probability of B. So putting that all together, we have probability of B being, basically 2 times of that. Probability of A given B is equal to 0.99 times 0.01 multiplied by 2 times of 0.99 times 0.01. And that's how you get to your answer of 1/2. So pretty, I don't know, counterintuitive maybe, because at first, like I think the natural non-mathematical answer to this question of, if a patient tests positive, what's the probability that they have the disease? You would think that, yeah, if I test positive, there's a 99% chance that I have the disease. But no, if you test positive in this scenario, there's only a 50% chance that you actually have the disease. So I think it's helpful to know, especially when you see these numbers of like efficacy rates and things like that. Good to be, I don't know, think critically about this stuff. But yeah, that is the process of solving a Bayes' theorem and law of total probability question. I know that was a lot of math. I will also admit that I've done like maybe like hundreds of questions like this in my lifetime. But yeah, any thoughts or questions about this before I go on to the next thing?
Is that just because the test, the 2 outcomes of the test case are pretty simple? It's either yes or no. Is that why it's kind of half? Because you're not taking any other effect size or any other false positives or doing any further testing towards there being a possibility of something else going wrong. You're just looking at it at its very base level of positive or not positive.
Oh, good question. I think the fact that this answer came out to be 1/2 has less to do with the fact that it's a binary outcome, but actually more to do with the fact of this number over here, more to do with this 0.01. The fact that there's only 1% chance that there's only 1% of the population that has this disease. Therefore, if a random person was to go take a test, and you also have to remove the idea of okay, I don't have symptoms or anything. I don't know if that maybe would complicate things, but it's the reason why this probability is so large is mainly, if you work backwards, it's mainly due to this probability of A number over here.
Yeah, well, because I was looking, because if you're looking at it, if you look at it just from a simple math theory level, because when you do math theory, you would take all these variables out and you just work with the long green thing that you put on the right.
Yeah.
Because it is 1%, you're essentially doing a test where it's pretty much yes or no, because the probability of it being a false positive or a false negative is so low because it's 99 out of 100. Because the chance of there being a false positive or negative is only 1%. So from a theory standpoint, it should be 1/2, correct?
Correct.
Because you've taken all other, essentially, you haven't, but you have taken all other scenarios out.
Yeah.
Just by making the chance, because if that was a 0.5, then you would have to do t-tests and you would have to do other evaluation, because that number would not be 1/2, because the chances would just be greater.
That's right. Yeah. Yeah, I would say that you start to see the relationship between test accuracy as well as, the population proportion, as well as, the flipped probabilities as well. I would say definitely try out that the other question that I have, the other one that's on the concept questions, because that one has a bunch of different false positive and false negative rates, and you can sort of see based on the outcome of it how the result relates to these inputs.
Yeah, because I was just thinking along those lines when it did come out to 1/2. I was thinking along the lines of, from a theoretical perspective, because if you're just going conceptual, because the probability of A and probability of B are basically as close to 100% as you're going to get in a simple way, it kind of keeps it in a theory. It keeps the theory without us having to sit and look at just letters and variables.
Yeah, that makes sense.
Basically.
Yeah.
Because I mean, if you're looking at it in the grander scale of testing, where you'd have to look for like false positives or other outcomes that aren't A or B, the chances of it not there being another outcome are pretty slim, just because of it being 1%.
Yeah, that's right.
Yeah.
Cool. Yeah, definitely. I feel like find out, like try and, I mean, of course, probability is not the most important thing for data scientists, but if you have the wealth of time to like spend some time thinking how you best intuitively think about probabilities, I think that will go a long way, because figuring out certain things, like for me at least, figuring out thinking of conditional probability this way, which is not, it's not a conventional way of thinking about probabilities, but figuring out these like little ways that are intuitive to you yourself, it's really going to bring you far, I think.
Yeah, because I when I thought about that and I saw that on the document, it kind of made me think that this one more so than the other ones was just basically getting the concept of the theory down, because rather than to give us something to calculate other than the way a mathematician would do it, which is just to give you all of these little variables and have you solve for variables.
Yeah.
Because that's just the way math people like to work.
That's true. Yeah, I myself was a math major, and that's why like I very much took a lot of like formulas that were just given to me for granted. But it was really until like I had to apply these things into real life where I was like, oh, okay, why do I use this formula at this time? Which was a little harder.
Yeah, I remember doing physics. When you do conceptual physics, you don't have numbers unless they're a constant, a universal constant. And then even then, they're generally represented by a letter.
That's right. Okay, any other questions on this topic? Because I do want to spend some time talking about MLE, which is super interesting. Okay, cool. So this other concept that I want to talk about today is MLE, which stands for maximum likelihood estimation. And to explain those things, I want to do a little bit of a review of probability, which we will do on this left side. And then we want to compare this to likelihood, which I'll do on this right side. So quick probability review. Let's just say we have this normal distribution right here, not drawn to scale, but let's just say that this is a normal distribution centered at 20, and there is a variance of 4. And let's just say this is X, and this is a PDF. So this is just the probability of X. So how do you read a diagram like this? Let's just say that this is, I don't know, the weight of puppies. That's the weight of all puppies in the world. I don't know what puppies weigh on a global scale, but let's just say this is the weight of puppies. And if I wanted to see, okay, what's the probability that my puppy weighs 24 pounds over here? The way you find out the probability is you kind of trace it over here and figure out, okay, that's the probability that my puppy will weigh 24 pounds. And let's just call this P1 for, I guess, probability 1. The way that you represent this in a mathematical notation way, and we're also going to re-bring in our our conditionals. So what this is saying is that the probability that X is equal to 24, given that X follows a normal distribution with parameters 20 and 4, meaning that mean of 20, variance of 4, is equal to P1. Does anyone have any questions about this notation? What I'm saying here is that given that this is the assumed distribution of puppy weights, P1 is the probability that your puppy weighs 24 pounds. Questions about this? This is important to like internalize before we move on. Okay, cool. So this is probability for pretty much any weight of puppy. You can figure out the probability. So like, let's say I want to figure out if I have a puppy of weight 19 of course, because 19 is closer to the peak of 20 or closer to the mean of 20, the probability that something will be 19 is going to be higher at P2. So that's just how you read a CDF. Typically, you don't write this given part because that's just assumed. But if you want to be very, very comprehensive about your probability, that's how you would write it out. Given that you know your puppy weights, or you're assuming that your puppy weights follow this distribution, the probability of having a puppy weighing 24 pounds is P1. Probability of having a puppy weighing 19 pounds is P2. Okay, so hopefully that is clear. Let's talk about likelihood now. So likelihood, I know in like plain English, the words likelihood and probability seem that they are interchangeable in just like regular English language, right? Not the case when you get into statistics. And this is actually very applicable to all of the modeling work that we're going to do starting next week. So I will say it's pretty abstract, but it's something that gives you an intuition for why modeling is the way it is. We'll get to that in a little bit. Okay, so let's just say that similarly, we have our puppy weights and puppy weights X. So likelihood is sort of like flipped probability. Let's just say that we have this same puppy here at 24 pounds. Cool. And then the whole idea of likelihood is given a small sample of data, we want to make some inferences on the population. So this also ties back into modeling, which we will get into more next week. But this is how the idea of likelihood comes about. So let's just say we have our one puppy. Let's just say we just have one puppy to start, and that puppy weighs 24 pounds. Using this one puppy, I want to try and guess, what does the global population of puppy weights look like? That's one way that you can think about likelihood. I have this one puppy that weighs 24 pounds, and let's say I have zero information about puppies all around the world. I just want to make the most educated guess based on this one puppy on what the population of puppy weights looks like. So to start, let's just go with the distribution that we had back here. So let's just guess, okay, what if, based on this weight 24 puppy, maybe I guess that that the weight of puppies is distributed like this, at a mean of 20 with a variance of 4. So where likelihood comes in is that, okay, we can sort of read it very similar to how we read the PDF. So we read 24 over here, figure this out, trace over here, and we end up with a likelihood 1. So mathematically, when we write it out, what does this mean? So instead here, we're going to do P, actually not P, we're going to do L for likelihood, but interchangeable as well. Okay, so likelihood is saying that given that we have this puppy of weight 24, X follows a normal distribution of 20, 4 with the likelihood L1. I know that's pretty abstract, but let's think about it a little bit. Given that we have this one data point of a puppy weighing 24 pounds, the probability of the population of puppies being distributed like this is going to be L1, which L1 will evaluate to be the same as P1. Whatever that number is, it would be the same, but the probability is flipped. The probability that the distribution of the population of puppies is this, based on this one puppy, is L1. So cool, that is likelihood. Does anyone want to clarify anything? Okay, so this topic,
So if you just have that one puppy, how would you have the assumption that the average puppy weight is 20?
Exactly, right? That doesn't make sense, right? So we're gonna get to that.
Okay.
Yeah, right now we're just making a wild guess, like uneducated based on, I guess, this diagram that we have here. So yeah, it doesn't make sense that why would we guess that it has a mean of 20. So yeah, so this is where we're going to talk about maximum likelihood. The whole idea of modeling, which we'll get to later when we talk about actually modeling, is we want to maximize likelihood as much as possible. So just as Naomi was getting to, like, if we have this one puppy of 24, why would we guess that the population is centered at 20? We can get to variance later as well, but it makes sense that if we have this one puppy of this 124-pound puppy, that we would guess, yeah, it makes sense that most puppies are 24 pounds, just based on me not having any knowledge on other puppies. It just makes sense for me to guess that the population of puppy weights will look something more like this. Just imagine that was symmetrical. And then therefore, the likelihood of that will be just much higher. L2 would be up here. So based on that, the likelihood of X following a normal distribution of 24,4, given that, oops, what's going on? Given that we have our point of X equal 24 is equal to L2. And in this case, L2 is greater than L1. L2 is right at the peak of our normal distribution curve. And because it's at the peak, we have essentially maximized our likelihood. So it makes sense if we just have one puppy, if we want to maximize our likelihood, we should make the educated guess that the distribution of puppies is centered at 24. So any questions about that concept of if we just move our curve, the likelihood goes up? And where we move our curve to depends on what data points we have in front of us. So, okay, assuming that this makes sense, let's just say that we have more puppies. We have this puppy of 24. Let me just get rid of this for now. With this puppy of 24. And then we also have, let's just say we have an influx of like a bunch of new puppies. And we have a puppy here. Oops, oh my gosh, I did not mean to delete that. Here, let me draw that back. There we go. Okay, so let's say we have a puppy here, one here, and a bunch around here. So let's say we have a lot of puppies over here. So based on this new information, where would you think this curve would go? Based on us getting all these new puppies centered around, let's just say that this is, I don't know, 22. It makes sense that because we have a bunch of puppies around here and a few outlier puppies like out here and out there, it makes sense for us to guess that the population of, oops, let me just draw a better curve. Makes sense that the population of puppies would look a lot more like this. And we're maximizing our likelihood with a bunch of different points, because earlier when we only have one point, yes, we maximize our likelihood over there. But now we have all of these puppies that we can get very, very high likelihoods for on this curve, there and there. And of course, there are ways to optimize for this, but that's not important right now. The thing that's important to note is that we can sort of maximize likelihood of what our population distribution looks like based on our sample like this. You can actually prove this mathematically, but it's not important for us at all. That to maximize likelihood, the mean and standard deviation of the population that you are guessing how likely it is going to match the population and standard deviation, sorry, the mean and standard deviation of your sample. So it makes sense, right? If you have like a bunch of points and if like the mean of your sample is 22, it makes sense that your likelihood will be maximized if your population also has a mean of 22. It kind of like also brings back some like central limit theorem thoughts too, which I think is pretty neat. But yeah, any thoughts on that as I write out mathematically what this would mean? Cool. So what this means is the likelihood of X following a normal distribution of 22,4, given that X has all of these points, you have like, I guess 119, 120, a bunch of like 22, a bunch of 22s, so on and so forth, and then like a couple outliers, is maximized here. Cool. Any thoughts or questions about this? All right. This is, I will admit, like a kind of abstract concept to grasp right now. But from here, I do want to talk about what we're about to do with our linear regression in our project. So before I get rid of this, last call for questions on this concept. The idea is we're trying to fit the best curve, the best normal distribution to our sample data. That's one way to think about it as well. Based on our sample data, we're going to try and make an inference, or we're trying to guess what the best population curve is. And we are using maximum likelihood to make that educated guess. And also notice that every time we have new information, that guess can change.
So in the last revision, when you have all the puppies and you have X equal to what looks like dictionary brackets, but it's like this list of X values, what actual, how are you using those numbers?
Oh, like how am I like calculating these?
Yeah, is it a mean, or is it like,
it's
what do you
not
do
really
with
a
all
mean.
those?
So all of these numbers is sort of just like, this is more of like a set notation. I was thinking of more like a set. Given that we
Okay.
have puppies with these weights, I can maximize my likelihood if I guess this distribution. Likelihood can be measured in different ways. You can also just sum the probabilities of each one as well. That also works, but you just have to be consistent with the way that you're measuring likelihood. Then it's all just relative to each other.
This might be a little out of left field, but like, would mode work for this? Since you would have the biggest frequency of a certain amount?
Yeah, especially because we are, and here is another thing, we are assuming that the population is normally distributed. That is an assumption that I didn't talk about why we're assuming that, puppy weights are normally distributed. But mainly for this case, because we're assuming it's a normal distribution, the mean and mode would be the same. So yeah, that's not out of left field.
So from a coding sense, that set would be where you would do the +1 counters until you iterated through the entire set.
Oh, like
run
how?
that, to
Got it.
calculate that out, if you were to code it, that's where you would iterate through each individual number of a set, and you'd use a +1 until you hit the end.
Like is your question asking how we would calculate where to maximize likelihood?
Yeah.
Interesting question. Technically, yes. You would do some iteration over all of your data points. The process of actually finding maximum likelihood is through gradient descent, which I think you might have seen in your pre-work. Correct me if I'm wrong, but we're going to get much more into gradient descent in phase 3. But it's actually through like a gradient descent procedure. If you don't remember what that is right now, if anyone is just like, oh no, what are these terms? Don't worry about it for now. But technically, yes, you are going to iterate over all of your data points. But for each, how do I phrase this without getting into a lot of modeling speak? For each assumption that you're making, there's a different way of calculating it. So for example, in this example where we're trying to fit the best normal distribution curve to our data points, there's one way of calculating it. And yes, that would involve calculating the probabilities of each point and then slowly adjusting to see where the best curve is. And by the way, we're not only adjusting for the mean, we can also adjust for the standard deviation, right? If we had like, let's say we figure out, okay, it's centered at 22. We can also try and figure out, okay, does it make more sense for the curve to look more like this, or maybe more like this? All different kinds of normal distributions. So yes, there is a bunch of iteration involved, but I wouldn't get too caught up on that. Like you would never, ever have to code this out.
Oh, because to code it out for maximum likelihood, you'd also have to find the opposite of the minimum. So then it would have to go, but you'd have to calculate the whole thing out rather than just one piece of that thing.
Correct. And it'll be a very much like trial and error process. I can't think of trial and error or gradient descent. We'll get to that more, but you can imagine that you're just going to try a bunch of different normal distributions, summing their probabilities and see, okay, is this one higher or is this one higher? So on and so forth.
That's where you get into the 3D modeling thing, because just like physics, there's, for everything you do on one side, something else has to happen on the other. And then, so you would never, like if you were doing for this particular thing with linear regression, you would never you would assume the likelihood, you wouldn't necessarily need to demonstrate it through a calculation.
Yes, that's correct.
You could just assume that it shifts that way and operate under that assumption, but to calculate it out would be a completely different analysis, essentially. Okay.
Yeah. I think the main point that I want to drive home about maximum likelihood estimation is you want to try and fit the best curve to your data. Yes, you're making some assumptions. Like the assumption that we're making here is like, okay, my population has a normal distribution. And in normal distribution, you have two different parameters that describe a normal distribution. You have your mean and your standard deviation. Maximum likelihood estimation is about the process of figuring out the best mean and standard deviation to fit your sample data.
Okay, so it's so basically in our context for this, the maximum likelihood is just a suggestion for where you might try another data point to get a better looking curve.
Yeah.
A different set of data points than the ones that you have to potentially plug in and get a better distribution than the one you have.
Yeah, the fact
Like
that you
if-
mentioned new data points is a really good point, right? Like, so let's say this is what we have at this point, but then we get another shipment of puppies, and let's say they're all down here, right? That would encourage us to probably shift our belief of our population.
Yeah, so if, say, for instance, the yellow curve, and you were looking at it, and you calculated out the yellow curve, but it was shifted, it was very pointy and not very well distributed it was very skewed to the left-hand side. You might think of just an estimation of where you might want to try something different, going to the maximum likelihood and seeing if that's too far to the right, maybe it's a little more central, and then that looks better for to test the hypotheses, but rather than actually a calculation per se.
Yeah. For every technique that we're going to talk about going forward, there's going to be a different strategy for it, and we will get to those. But yeah, it's going to be a very interesting next couple of months. But yes, absolutely right. I would say in this case, maximum likelihood, you are constrained by the fact that you're making the assumption that it's a normal distribution, because the only things that you can adjust now are your mean and standard deviation. If you want to completely change your belief and you say, okay, I don't believe that it's a normal distribution anymore. I believe that it's a distribution that looks like maybe like this. Maybe you have a bunch of small puppies, a bunch of large puppies. Then you completely start from scratch again. And then you have, I don't even know what kind of parameters you would do to adjust a bimodal distribution like this, but
okay, so
yeah.
So that's under the assumption it's a normal distribution, and then it would just be simply potentially using maximum likelihood to test if you can get a better looking normal distribution, essentially.
Yeah, exactly.
Rather than one that maybe is a little, a graph is a little too pointy and a little too narrow focused with too much on the outside and not covering enough of your points.
Yes, and I would say like the nicer looking is defined by whatever one maximizes your likelihood.
Yeah, and at which point, if it was too skewed and you were testing, say, your hypotheses, the sharper, pointier one is more likely to reject it than to come off as it might help you solve a rejection.
Ooh. I think I haven't really thought about it from a hypothesis testing standpoint. I have to like marinate with that thought more, but that's an interesting thought. I don't want to confirm or deny anything.
Yeah, not just like not a concrete thing, just an abstract of where you might want to start looking. I mean, you might find that it doesn't work at all, and then you have to go and shift it back, but just as a way of maybe trying to look at something different.
Oh, absolutely. I will tell you when we get to phase 3, it's going to be a lot of these thoughts. All right. I do want to talk about how this relates to what's coming up next week. So let me start with that. Clear all drawings. Okay. So what are we doing next week? Next week, we're going to do linear regression. I know we haven't gotten to any of it yet. I will also say that next week, no matter where you are at in catching up on the stat stuff, no matter where you're at, I want everybody to just stop with the stats and then get straight into topic 18. Wherever you're, let's say you're still a little bit behind, let's say you're still working on like topic, I don't know, 13, 14. I highly recommend just leave the other stat stuff for later and go straight into 18, because that's the part that's going to be most important for our project and also most important for data science. Anything that you will need to know about anything that you might have skipped over, I will go over again. So anything that's important from the previous topics, I will go over again in a linear regression context. So don't worry about that. That's a very important strategy. I think like students who delay starting linear regression, it's a lot tougher for the project. So just want to put that out there first. Okay, we're going to get into more of exactly formally what linear regression is, but to like concisely summarize, linear regression is for predicting a continuous variable. So let's just use our example of the provided data set that we had. The provided data set that we have for this project is the price of a house. So the price of a house. And this whole idea here is we want to build some sort of model to predict the price of the house based on some of its other features, which is why I say minimum 10 columns if you're trying to find your own data set. So in this case, we're going to simplify. Let's just say that we're trying to predict the price of the house using the square footage. So how do we do that? We just collect a bunch of sample data. Let's just say we have housing data sets, and then we pick out some points that we want to build our model on. So let's just say that, okay, it makes sense that houses with lower square footage have lower prices, but they are going to vary because there are other things as well. Maybe some are in nice locations, some not, I don't know. So you're going to have a bunch of like prices of houses, and they're not going to follow a straight line. Definitely not. They're probably going to be like scattered all over the place, maybe some general trend. That's up to you to do your EDA and find out. So let's just say these are all houses with their price and square footage. The whole idea of linear regression, I'm just going to draw more points while I do this. The whole point of linear regression is to figure out the best line that fits through these points. And we'll get into more like data science-y how we do that and why we do that. But in building a model to figure out price of a house based on square footage, let's just say we have this line over here. Oops, where's my line? Line over here, okay. So this is a line that we create based on the assumption that square footage and price are linearly related. So we have made this assumption that square footage and price are linear related. Therefore, we want to do this linear regression. So that's one of the assumptions, similar to how earlier we had the constraint that the population of puppy weights is normally distributed. So based on this, we can now use this model that we've created to predict other housing prices based on their square footage. So for example, let's say we have a house with, I don't know, X square feet. Based on this model, we're going to use the straight line and predict, okay, this house is X square feet. It should cost Y amount of money. And based on this model that we've decided on based on our training data or our X data points, this is the model that we have. We'll get into more details about this tomorrow. But the thing I want to get by is for maximum likelihood estimation, oh man, I want to delete all of these. Maximum likelihood estimation helps us decide on what is the best line, right? Like there's a different way of calculating likelihood in this case, but this line looks like it makes sense. What if we have a line that kind of looks like this? To some degree, the blue line also looks like it might make sense, but it's this whole process of choosing the best line. That is what we're going to go through. What is the best line that we're going to use that is going to be reliable for predicting other housing, other prices of houses? So let's say we want to build like 3 new houses priced here, here, and here. Would it be more accurate to use the blue line or the red line? That's kind of the things that we're going to be thinking about going forward. Any thoughts and questions about this?
So this is basically just the same as physics and calculating the best tangent slope line when given a giant set of experimental data point.
That's exactly what we're going to be doing.
Except you're just
kind of.
predicting something that isn't there rather than just calculating it.
Correct. And we'll go through all of the processes next week. If you're curious about it, feel free to I don't know, read ahead at your material. My project 2 guidelines doc is already up for you to look at. But yeah, we're going to basically go through this process of building a housing price prediction model, or whatever data set you choose to find. We're going to work on that. Oh yeah, and I guess quick note, if you have been speaking with your project partner and you do want to choose your own data, you have to let me know, just so I can take a look at the data set and make sure that's feasible.
Can we use more than one factor, or it has to only be one factor?
Absolutely, yes. You definitely want to use more than one factor. This is just because I cannot draw in multiple dimensions, but yes. For your project, you want to use at least 10 factors.
Okay. That makes sense.
And how we're going to do that, we'll get to next week. Cool. Anything else?
It's basically just regular science.
Yeah. It's so interesting.
I thought from having been in computer and taken physics and wanting to be an engineer at one point, I thought this looked familiar.
Yeah, I will say, I know there's a few econ majors in this class. I was also an econ major. And so I did this in econometrics, where I had to calculate everything by hand. And then good thing about Python is we don't have to do that by hand anymore. But in thinking about, just through the data science lens, you think about the same problem just very, very differently.
You don't have to do calculus, because you don't have to calculate a tangent line, because the data points don't make a curve.
Technically, in the method will do it for you. We'll get to that as well. But yeah, you literally just write 2 lines of code, and it's really all about interpretation. But we will get to that next week. But yeah, I know this is a lot of stuff, very conceptual. I think it's a good setup for what we're going to do next week. Again, highly recommend, just if I actually would prefer you all get a head start on topic 18 rather than trying to finish up more stat stuff if you're doing anything over this weekend. Cool. Any thoughts, questions, comments? All right, I'm going to stop the recording here.